Hey, welcome back. My name is Bertel Schjerning. I'm from University of Copenhagen. And so what I'm going to do now is I'm going to try to tell you how to do maximum likelihood estimation of dynamic discrete choice models. And we're going to start with single agent models. Very, very simple, Harrow-Zucker engine replacement. And then we add a little bit more features on. And in the end, we're going to estimate them with the equilibrium constraints, where they're going to be like prices, the clear markets of, cars that we're going to look at. It could be engines on Harrow-Zucker's machines. So that's the plan. And unlike Bob, I'm going to do a full solution method. Okay, so before we learned we could estimate the models without solving them, but now we're going to estimate models like repeatedly solving. That's kind of the idea about this nested fixed point algorithm. Okay. Okay, so we're going to start with, just get all the mysteries away. Who's Harrow-Zucker? Okay, this is Harrow-Zucker. He's like the superintendent of maintenance in bus company in Madison. Okay, so he's the guy that John got the data from on engine replacement models. And yeah, so he passed away, but he got like 94 years. It's almost like infinite horizon, right? So he was making monthly mileage decisions. And so yeah, I think that infinite horizon model you'll see is probably a good approximation for his planning horizon. Anyway, so yeah, who cares about Harrow-Zucker? Of course, his family does, but whole lots of papers is building upon this. Okay, so it's like this is not even updated, but this occupational choice and retirement, and brand choice and advertising. There's so many discrete choices out there, and in the end, I'm going to go all the way to 2022, where we have a paper, Ken Gillingham, John Rust, Fedor, Anders Munk-Nielsen, and I, about car replacement or car trade. Okay, so we'll look at that at the end. And that's a model with this equilibrium constraints and more choices, than just replacing and not replacing. So yeah, and then many more citing this. And this is like the citation curve of this engine replacement paper. So it's kind of still upward trending. Okay, so lots of people are doing structural work. Anyway, so just to kind of get ideas fixed with this model, Bob presented a slightly different version of the model with no uncertainty about the driving every month. So I'm just going to, just for completeness, put up the model here from the original paper. So this binary choice, so the choice set is 0, 1. Okay, if you replace the engine, D is equal to 1. If you just do ordinary maintenance, D is equal to 0. And then Harrow-Zucker here observed these two state variables. Okay, so there's both observed state variables, X, and then there's the epsilons that are same as Bob's epsilons, right? It's like these unobserved state variables that we don't observe as econometricians, but Harrow-Zucker here observed and bases his decisions on. And so the observed mileage, or the observed state variable, is going to be the observed mileage since last replacement. So that's kind of, every time he replaces the engine, he just put the mileage back to 0. It's like brand new engine, brand new bus. It's like as good as new, okay? And so there's a payoff function because it's not free just to replace the engine. You have to pay the replacement cost, or RC, and that's a parameter we'll like to try to see if we can estimate. And then there's a maintenance cost function here. There's a function, properly increasing, right? In the mileage on the bus. Every time a bus is old, all these gaskets kind of blow, and all this kind of stuff. Probably if you have a car, you kind of know the feeling of having an old clunker, right? So that's going to be increasing. We're going to parameterize that. You can put in like a linear function or quadratic or whatever. Okay, and they'll try to see if we can estimate the parameters θ1 of that maintenance cost function. And then the state variable process, we can assume epsilon is following this conditional density. Mileage has this regenerative random walk. So every time you replace the engine, that's D equal to 1, then the mileage this period is D put equal to 0. And then the innovations every period is going to be how much are these buses driving. Okay. And so what we want to do is we want to estimate the structural parameters RC, theta 1, the utility parameters, and then the parameters theta 3 that indexes this state variable process, what Bob is calling F. Okay, we're not going to try to estimate this theta 2 because that's the parameters that's indexing these shocks, and later we're going to just assume they are the extreme value. There are no parameters there. Okay, we need to make this scale normalization and so on. But if you have like a nested logit, well, it doesn't make that much sense in a binary choice model, but that would be the parameters that enter. Okay, so we're going to fix the other parameters. Okay, but before we even get to that point, let's talk about how to actually solve this modeling, set it up. So we're going to write up, here's the Bellman equation. What's going on with this? I don't know. Yeah, maybe some loose connection over here. Looks pretty firm to me. Anyway, we'll try to see if how it goes. Okay, so here's the Bellman equation. So Harold Zucker is making like these binary decisions, and more generally, it could be like more choices, 1, 2, 3, 4, 5 up to capital J, different choices in some state-dependent choice set. Depends on the state of the world today. Okay? And then your derived utility, and then there's a future expected utility. Now this expectation is taking over next period values, okay, given this state variable process. Okay. So let's have a look at this little beauty. How do we even compute the right-hand side of this equation here? Because we want to solve, if we want to solve the model, we want to solve for the value function so we can calculate the conditional choice probabilities afterwards. Okay, so how do you find that fixed point? Well, we just start doing, guessing a value function, putting it in on the right-hand side, and then you just, iterate until convergence. But just, evaluating the right-hand side is already pretty difficult, right? Because this is like a high-dimensional object. So first thing, x, it's a continuous variable, okay? And epsilon is continuous too, and it's like j-dimensional. So if you have many choices, it's going to be like many state variables, okay? So this is a very high-dimensional object, potentially. And so also evaluating that expectation here, the conditional expectation, requires very high-dimensional integration, okay? You saw all the integrals over epsilons before, okay? So that's pretty bad. And just even evaluating that value function may require, if you just take this problem head on, require like high-dimensional interpolation, right? Because you've got a function that's high-dimensional and depends on a bunch of continuous state variables. If you want to evaluate it between, well, you need to do high-dimensional approximation or interpolation of this function over these many state variables. And then beyond that, it's non-differentiable. Okay, so if you want to do maximum likelihood, derive the likelihood function based on this, use your favorite gradient-based solver, it's pretty hard, right? So, okay, so that's where you go. Okay, so this is what John did to simplify this problem. So we're going to assume additive separability of the utility function. So those epsilons, those state variables, unobserved state variables, is going to be additive in the payoff function. Second one is the conditional independence, and we already heard about it, right? So, for example, it means that it factors the state transition process for x and epsilon conditional on d. It factors into these two terms here. And for example, there's no dependence on the current epsilons and the future epsilons. You can't have serially correlated errors here. Okay. And then the third one is going to assume that the epsilons are the extreme value. Okay? That makes things much simpler. Okay, so we'll just take our Bellman equation here and try to see, okay, what does those assumptions do to this Bellman equation? Well, the additive separability and conditional independence allows us to separate out deterministic part of the Bellman equation as these, I think, call them choice-specific value functions. Okay. And then we can reformulate the Bellman equation in a much reduced space, so we don't have to work over this huge space and solve for a fixed point over these, the x's and all these j-dimensional epsilons. Okay, so we can work with the expected value function and sometimes the integrated value functions. And then we get from the extreme value, we get the closed form conditional choice probabilities, and we get also closed forms for expectation of the max. So that kind of rules out the most difficult part of that integral. Okay, so here we go. Okay, so all I've done here is just, I've rewritten the Bellman equation, and then I've used the conditional independence assumption, kind of, substituted that in, and then I put this, the state transition process for the observable state variables outside the bracket, and you can kind of already see here, and once we integrate out those unobserved state variables, nothing here actually really depend on anything but the observed state variables and the decisions. Okay, so from that perspective, conditional on X, conditional on observed states, a Mile-Ridge and a decision, everything here is really, deterministic. Okay, and then you have this additive epsilon. Okay, so we can write this Bellman equation here in this particular form, where you have these choice-specific value functions without the shock, and then just add the shock outside. Okay, now it starts to look like a standard random utility model. Right? Okay, so let's move on. So that was kind of the first thing. Okay, now we can. The tricky thing is that still this expected value function is still defined over the space of epsilons. So what can we do? Well, we can just work with the expected value function. Okay, so that's it, that value function, but only we're taking expectations conditional on the observed state variables and the decisions. Okay, so let's call that the expected value function. And then because of the conditional independence assumption, we can now express this the Bellman equation here in terms of the expected value function in this particular way. Okay, so here I'm just essentially taking that conditional expectation. Okay, and so what you should notice here is, what is this? Well, it still depends on x's, right? Oh, it still depends on epsilons, but those epsilons, well, they'll be integrated out, and in the end, they're just going to be additive. Okay, so then you have this mapping essentially from expected value functions to expected value functions. So if you know what EV is, you actually solve the model. We just need to take that integral over that max. Okay, and like you kind of, I said they were going to be at extreme values. So in a second, that's going to be a closed form. So that's pretty useful, because now this new Bellman operator defined on the expected value function space, well, John shows is a contraction mapping, and in principle, you could just solve this equation by iteratively, iterating on the Bellman equation. You guess an expected value function, you put it into the Bellman equation, get something out, you put it right back in, you iterate until convergence. Okay, so you're going to get like a unique fixed point in this expected value function, which is nice because now this expected value function is much lower dimensional. Doesn't even depend on the epsilons. There's an alternative representation I also just want to show you here. Is you can work with the integrated value function. Sometimes they call the smooth value function. What's wrong? There's a question. Okay, yes?
Reversible metric is a contraction mapping, and like why is that intuitively the case that it's a contraction mapping?
Well, there's a proof, and I guess it's on some sort of Banach space or something. That's above my pay grade. I guess you'll have to read some of John's proofs about that. Yeah. Actually, we're going to discretize the whole thing, so it's not going to be a functional space once we kind of implement it on the computer. Anyway, so let this V bar denote the integrated value function. And so now we can also express this Bellman equation in integrated value function space. Okay, so that's just taking the expectation of the value function conditional only on x. Okay, and so what we're going to do is we're just going to integrate out the epsilons. Okay, now again, this value function here has the same form, but now we need to take the additional integral over the observed states. Okay, but still, this is a mapping from integrated value functions to integrated value function. Again, it's a contraction mapping, and I think there's a proof also by John Stakursky that shows all these things are equivalent. So that's also a contraction, which means that now you could do successful approximations in the integrated value function space instead of working with this huge animal. Okay, so, well, it doesn't even depend on the decision. That's important if you want to approximate these value functions over the state variables you include. If you have like a linear interpolation or use, I don't know, Chebyshev polynomials, or nowadays, use neural nets or something. Okay? Then it's important that this is a small dimensional space. So we really get a lot from that conditional independence and also from the extreme value that I'm going to show you here. Okay, so last thing, we still need to take that expectation of the max. Well, but once you assume this epsilon here is at extreme value, you can compute that in closed form. So that's this log of the sum of the exponentials of the choice-specific value functions without the epsilons. Closed form, just a sum. It's completely smooth. Okay, it's just a sum, logs of sums of exponentials. The choice probables, well, they're going to be multinomial logistic, also closed form. So no integrals in calculating that, taking integrals of indicator functions, whether this was the optimal choice. So this is a huge benefit. And this is part of the reasons why we're doing it. It's have this huge computational benefit. So it avoids this J-dimensional numerical integration, and beyond that, we got the conditional choice probabilities in the integrated and expected value functions. They're all smooth functions of the primitives of the model. You change the parameter, they change smoothly. Okay? Okay. So yeah, so you put this together. Here, you get conditional choice probabilities like this, okay? So they are this Logit formula. What I want to highlight here is that now this expected value function, what is that? That's a fixed point of this Bellman operator, okay? I put a little subscript theta here. Why? Because, these are implicit functions of the parameters. Every time you change theta, well, you're going to change, for example, utility function, okay? That's like changing the Bellman operator, okay? If you change also, if you change the parameters of the state transition, well, you're also changing the Bellman operator. Well, so the Bellman operator depends on the parameters, and so the fixed point is going to depend on the parameters as well, right? They're like implicit functions of these parameters, okay? And therefore, also, of course, the conditional choice probabilities depends on the parameters. So, well, I'm not going to do neural nets or Chebyshev polynomials. I'm just going to do like John. We discretize all the state variables. Okay, so just figure there's a finite number of bins for mileage, 1 up to 90 or 100 or 175 or something. Okay, which means that now the distribution is also discrete. So rather than going through this, I just want to show you. This means that there's like a state transition matrix for each of the different choices. Here we only have two, right? We have replace and keep. So let's have a look at this little baby here. This is the state transition matrix for keeping the engine. Now every month, these buses are driving a little bit, so there's a probability you move up to the next bin. Okay, so here you got the states today, and then in the columns you got the states tomorrow. Okay? And then we are conditioning on the decision. Okay, so you start with a brand new bus, for example, and then with some probabilities, it drives and goes up to the next bin. Okay? I think In the model that Bob was showing, that would just be like a 1 on this off diagonal. Just always drive, except for probably in the last bin, it just stayed there, okay? This zero is below the diagonal. Why do you think that's the case? Why is the zeros below the diagonal? They don't drive backwards, right? Okay, that would kind of be a little bit weird. And then you also have like zeros at this off diagonal, because it's kind of limits in how how long these buses are driving every month. So it's like, I think the largest value in the state space is 400,000 miles or 450,000 miles. That's a little bit long to go in 1 month, right? So that's conditional on keeping. Now, if you replace, well, essentially you get back to the original. So it's like the distribution of states tomorrow is going to be the same as if you had a brand new bus. That's why you have this column. Okay. Now you can easily just implement this on the computer with simple matrix operations. Okay, so here's a Bellman equation in matrix form. Okay, so the expected value function is going to be now this state transition matrix here times this expected max, which is the log of the sum of the exponentials of the choice-specific value functions, which we have right here. Okay, or you can have the alternative formulation where you don't do that integration over the future states, where you work with the integrated value function, and then it's just going to be the log sum. And then, of course, you need to calculate the expected value function. So that requires this integration over how much the buses are driving next period. Just two different ways of implementing the same. And okay, here I've just omitted the x's. Everything is just stacked. Okay, so it's a matrix notation. We have like states down, decisions in the columns. Okay, so how do you estimate this model with maximum likelihood? Well, we get some data. That's where Harasaka comes in. Okay, so actually, I think, well, John is not here to tell the story, but he originally submitted this paper about the nested fixed point algorithm to Econometric, and then Angus Deaton say, well, I want to see you can do this in the real world. You give me an application, and that's where he was like searching for data at various different places, rental car companies and whatnot. Nobody really wanted to give him the data, and then he met Harasaka. Okay, that's kind of where it all started. Okay, so you got data on Harasaka's replacement decisions, and then the observed mileage every month comes into maintenance, and then he writes down, and then looks what is the mileage. Okay, so here's a likelihood function. Well, we sum over all the different buses, but the likelihood contribution consists of two things here. Okay, so it's first is the log likelihood contribution for the state variable process. So that's pretty standard, doesn't depend on dynamic programming. So let's focus on this guy over here. It's a log of the choice probabilities evaluated at the data. Okay, it's just simple discrete choice. And now we just need to evaluate this logit formula here. But in turn, it actually depends on these expected value functions that in turn depend on the parameters. So what do? Well, what you do is if you want to maximize the likelihood function and estimate the structural parameter theta, you search over the parameter space, but then every time you evaluate the likelihood function, you have to go calculate the conditional choice probabilities. Oh my God, you need to calculate the fixed point. So you repeatedly calculate that fixed point. That's kind of why it's called the nested fixed point algorithm, because you need to, like in a nested loop, calculate these fixed points. Okay, so that's kind of, in the nutshell what the nested fixed point algorithm is about, right? So the nested fixed point algorithm is it's unconstrained optimization problem where you maximize this likelihood function here with respect to the parameters, and then there's this outer hill climbing algorithm that's like BFGS or Newton's method or whatever you can come up with. And then each evaluation requires doing some sort of inner fixed point iteration. Okay, you need to solve the Bellman equation. What John is doing two things. He's doing what we talked about already, like successive approximation. You guess a Bellman equation, you put it in, or you guess a value function, you put it into the Bellman equation, you iterate until convergence, and then you got your fixed point. Or then you change parameters again, you do it again and again and again, okay? Now that takes a lot of time, okay, especially for big models. So he figured out that you could also do like Newton's method. I'm going to show you later how to do that, okay? And then for the outer loop, well, you can actually exploit, this is maximum likelihood. So it's something called the BHHH algorithm, which is using the information identity from maximum likelihood to do an approximation of the Hessian. So that's really powerful, actually. Okay, so now we got results. You know how to do that. And so here are the results that you can estimate all these replacement cost parameters for this particular dynamic model with, Harold Zucker is very forward-looking. His discount factor is 0.9999. And then you can estimate the replacement cost. And here we work with a linear cost function. Okay, so it's just one parameter, and that's a parameter here. Okay, there's different types of buses and so on. Okay, now if you want to do this yourself, there's actually some code in the repository where you can do this. This is in MATLAB, and there's also some exercises in Python that you can kind of go through if you feel like. Okay, so I just want to kind of convince you that the code actually runs, and this is where it could be very embarrassing. Okay. Well, it did. Okay. So you see, it didn't take so much time to estimate Rust's model here. Okay. So, we did it in like, 0.9 seconds, 0.19 seconds. Okay. And what it's doing here is doing all this machinery with this nested fixed point algorithm, searching over the parameter space, evaluating these fixed points again and again and again. Okay. But it's also a small model. Okay. Anyway, so that's run bus data, and you can essentially replicate these results from his paper with that. Okay. Now, here's why we actually might want to do maximum likelihood in this case. So here's the Meyerich since last replacement. And this is a non-parametric hazard. This is the frequency estimator of the conditional choice probabilities. Okay, we just divide them into like 90 bins or something. Calculate what's the fraction of people or the times that Harold Zucker would replace an engine with, I don't know, so and so many miles. Okay, you see, it's kind of a little bit wiggly. Of course, here you can estimate these conditional choice probabilities, putting some more structure on that, just using the frequency estimator, you do like a flexible logit or something. But it would probably be a good idea to impose some structure. Okay? That's what we do. Okay? We're going to impose the structure from Harold Zucker's optimization problem, not just from a flexible logit. Okay, now once you've estimated that model, you can calculate what is the equilibrium demand for engine, and you can do demand curves. So, the conditional choice probabilities together with the state transition, that gives, in this case, like a macro transition matrix for this control process. Okay, both taking into account Harold Zucker's optimal decisions and then how much is kind of driving these buses exogenously. And then you can find the ergodic distribution to that matrix, and then you got the distribution of Meyerich. You can also calculate conditional on replacement and not replacement. We're going to work with that later in the car model, because we're going to work with the ergodic distribution of cars of different types different types. And then you can calculate, so here it is. Here's the equilibrium distribution of Meyerich for those that are just replaced and those that are kept. Here's like a demand curve, and it's an example. It's an example of a counterfactual. You just change the parameters and see, okay, what happens to the demand for engines. And you can see here the demand curve for the static model where beta is equal to 0 is much steeper. because not taking into account the future. Okay, so that was all about NFXP. Okay. Now there's another way of doing this. It's called mathematical programming with equilibrium constraints. So our MPAC. So it's actually, think about it. You want to maximize the likelihood. You just want to make sure the Bowman equation holds. Okay? Now the way John was doing it was like repeatedly solving this every time you evaluate the likelihood function. You can also just think of it as a constraint optimization problem, which is what Sue and Judd did. So they had a paper in Econometric had for like a decade ago, where they tried this out. They have various different implementations, both with in MATLAB and in a high-level programming language called AMPL, where they are implementing this constraint optimization problem. And I think the message here is you should really let the computer guys do the computing part, like calculating automatic different derivatives, utilize the sparsity patterns, and so on, and that's still going on that AMPL. Okay. Nowadays, you can do this also like in Python, right? There will be libraries like JAX, and you know about JAX, you should talk to Max. He's right there in the back. He knows. You would call him JAX Jesus. He knows all about that. That has automatic differentiation. Okay. Anyway, so let's just compare to what they did. So they're going to do a little Monte Carlo. So we're going to simulate some data from a model similar to the parameters I just showed you. So from this table 10. Okay, so it's going to have a fixed point dimension. That's the number of grid points. 175, a linear cost function, and then we're going to have these parameters similar to this table I just showed you. Okay, so this is like right here. So just simulate some data from this model. And here the state transition parameters, those on these band diagonal in these state transition matrices. Also assume that. And then we solve the model and simulate a bunch of data sets and see if we can estimate the model right back and make it like a horse race between NFXP and MPAC. And so here are the results. See, the nice thing about this AMPL is it actually does second order derivatives. Okay, so it's going to be much faster and it utilizes sparsity patterns. There's also a MATLAB implementation where you have to kind of code that stuff in your own and doesn't use the second order derivative, so it's a little bit inefficient. So let's just focus on the AMPL implementation. Okay, and then there's NFXP. So they do like a bunch of runs, so they do it 250 times with different starting values. So that gives, I think there's 5 different starting values that gives you like 1,250 different runs. And you see AMPL actually deliver the job most of the time, and it's pretty fast, 0.13 seconds. Okay, and so here's a number of major iterations, a number of function evaluations. So this is the number of times you kind of, you change the parameters in the structural parameters. And then there's NFXP. Not that good. Huh? Oh, sorry. The table is from Judd and Sue 2012. So that's it. That's the Monte Carlo they did. Okay. Looks like NFXP is pretty slow. Doesn't always work. And see, it's taking all these contraction iterations because you have to repeatedly solve this Bellman equation. Right? Every time you try a new parameter vector, it's just, do the successive approximations. And see, it only gets worse, right? As you increase the discount factor, we go to 748,000 contraction iterations, okay? 748,000, you need to evaluate the Bellman operator. Yes.
Is there a trade-off with impact when the choice space grows really large? It seems like it would be hard to solve like with many constraints.
You have as many constraints as you have states and choices. So, yeah. Well, but it's also hard to repeatedly solve the Bellman equation, right? And it turns out actually you solve this by Newton's method, they end up being actually quite similar in the computational complexity. Okay, so yeah, I'm not going to go focus on much on MPAC. I'm going to use this as a chance to focus on how you compute the the solution to the optimization problem, how you maximize the likelihood function using the nested fixed point algorithm. Because the key point I want to make here is that implementation details actually matters a lot. So those 748,000 contraction iterations, that's a faster way. Okay. So here's we'll call it like the CPR for the nested fixed point algorithm. Start reading the documentation and do exactly like we did, and that's what we did. And then there's some tricks you need to use, like recentering the logit formulas and log sums. Use this poly algorithm that John suggested of successive approximations and nested fixed point iterations. You need to auto-calculate analytic gradients, both of the Bellman operator and the likelihood function. Utilize it's actually differentiable, and you can calculate all these things in closed form. And then the BHHH algorithm. Okay, so that's kind of that's an agenda for the next couple of minutes. Okay. So, and then of course, if that's not enough, you just go back and read documentation again and see if you missed something. Okay, that's a plan. So here's the documentation. There's a nice documentation manual. This is version 6, but it's originally from 1987. Okay, 86, I guess, the first version. And we have a little comment where we kind of does a comparison. Anyway, so actually, if you look at the documentation manual, this is from 1987. It says John already see that you can solve this as a constraint optimization problem, but he emphasizes the importance of utilizing this unique fixed point here is an implicit function of theta, and you can get guaranteed convergence because of contraction mapping properties. And that's why he kind of preferred the unconstrained optimization problem that kind of led to the nested fixed point algorithm. That's what it says there. And what you also see is like this map over what to do with the nested fixed point algorithm. And what I like to do is I always almost always, not right now, have a copy on me because it's kind of, you print it out on A4, like fold a couple of times, it fits into your genes. You always know how to do the nested fixed point algorithm. Okay, so you start with a guess of parameters, initialize the thing, okay? So and then you start doing contraction iterations, okay? Now, if that's contraction iterations is sufficiently close, well, then you're gonna start doing Newton iterations. And that's what's going on here. And then you iterate until convergence. And see, the cool thing here, as you'll see, is that once you have done that, once you have computed that, you already have the derivative of the Bellman operator and the fixed point as a byproduct of the solution algorithm. And that allows you to actually calculate the derivatives of the expected value function with respect to a change in the parameters, which is what you need for calculating the derivatives of the likelihood. So all these things kind of fit nicely together in this little map. Okay. Anyway, so it's all there. So here's a little more practical details. Little things like, using exponentials. You have to do something to recenter the choice problems. Everybody, I guess, who worked with the logit formulas will experience that. If you just put in the expected value function or whatever the utility is, take the exponential, you quickly go out of bound with the computer. Okay? So fortunately, you can just subtract the constant. In some sense, it's like a continuation of what Bob just says. Only the differences in utilities that matters for the conditional choice problems. So we can just safely subtract that constant. Now if you take this as a max, for example, over all the different alternatives, you ensure you always get a negative number in here. And now the exponential of negative number kind of goes to 0. It's much better to have underflow than overflow on your computer when you calculate conditional choice probabilities, because then this would actually, if you have a probability that's very low for choosing it, you will get the answer it's low instead of just infinity divided by infinity. Okay, and so there's another place you need to do this when you calculate the log sums. Okay, it's like all these times you calculate exponentials of value functions, you better do that because otherwise it's going to explode on you. So that's one thing that needs to be done. That was not done in that implementation, and that's also why you see as the discount factor becomes, you know, closer and closer to 1, these value choice-specific value functions is going to be bigger and bigger, right? Because you're now discounting longer and longer future. So it's important to do that. Okay. Okay. So what about this Pauli algorithm? We're going to, you know, find a fixed point on the contraction mapping here, right? That's what we want to do. And here it's, you know, expressed in terms of the expected value function. Yes, that's a question.
Yes, sorry, so it's the previous slide. So when you do this recentering, right?
Mm-hmm.
So yeah, for this, like the essence would be the meaning of the estimates will economically change, right? For example, if you do this,
Nothing changes.
numbers will change, right?
No, nothing changes because this you can just, you know, you can show that these two here are just identical. This is equal to that, so nothing changes. This is equal to that, nothing changes. And you can, you know, it's kind of a nice exercise. Sit down with pencil and paper. You know, here you just take the exponential of VI times the exponential or divided by the exponential of V0. That just cancels out.
Require any normalization on the value.
This is not about normalization, just about recentering the Bellman equation. Yeah. Okay, so why don't we try to solve this? You can do successive approximations, you know, iterating on, you start guessing on EV, and, you know, you iterate, and then you get there eventually because it's a contraction. But see, the problem is this is linear convergence. So, and the rate of convergence depends on beta. So it's really, really slow whenever beta goes to 1, right? Which kind of makes sense. You're approximating essentially infinite horizon with infinite horizon problem with a finite horizon problem for a guy who's very forward looking. That's not a good approximation when beta is very close to 1, okay? So the rate of convergence is very slow. And then there's the Newton-Kontorovich iteration. Well, it does something different. It just takes this and solves a system of linear equations. It turns out that if you just, you know, rewrite this and solve for the zeros using Newton's method, you get this other iteration. Okay, so what is this? This is the derivative of the Bellman operator with respect to a change in EV. Okay, so you need to compute that. And then you just essentially take EV times the, you know, the EV after one successive approximation. Multiply with that, and then that's kind of the iteration. So this is where you start, and this is your step. It's just standard Newton's method. What is nice is that this is quadratic convergent. So as you get closer and closer, these errors is going to be smaller and smaller. Yes?
It's scary to take a derivative of the operator which maps functional space to functional space.
Well, right now we have implemented this on a finite state space. Okay, so it's essentially just a set of nonlinear equations. Okay, and it would be so if we were like doing some finite representation of the expected value function in, I don't know, you know, Chebyshev polynomials, a finite number of grid points, and then that will be same. Oh no, so yeah, sorry. It's just a derivative. Okay, so how does that look? Let's actually try it out. Let's try it out. So what I want to do is, this is run FXP. This is where I need my glasses. Okay. Didn't quite solve it, right? This is the tolerance. Maximum absolute difference between two successive approximations should be 0. Okay, so why don't we just take some more? Okay, so we'll, you know, just, I have a little bit of code over here. So I'll just increase the number of iterations, right? Eventually, you will be able to solve this, right? The size, yeah. I'll do that. Okay, now it's not 0 to machine precision. This is the error bound after 10,000 iterations. You can see kind of where is this, 748,000 iterations coming from. But now let's try Newton's method, this Pauli algorithm. And that's what we're going to do now. Okay. And then there you go. Pretty fast. Okay, so you start with some sort of successive approximation just to get into a domain of attraction. And what you see here is that the relative size of these is going to be actually pretty close to the discount factor. That's a sign that we're within some sort of domain of attraction because there'll only be a constant left. Then you have the Newton-Kontorovich iterations, 1, 2, 3, 4. You see the quadratic convergence. It's like this error bound is, first it's to, I don't know, to the power of -2 and 4 and 6 and so on, right? So instead of let's continuously continue to do successive approximations. So anyway, back to the slides. Okay, and that's how here I have plotted this error bound against the iteration count. Here's 10,000 iterations. This is for successive approximation. And up here we have like beta equal to 0.999, and you'll see after 10,000 iterations, not a lot of stuff happened, right? Of course, it gets better if you have a discount factor that's closer to 0. I mean, when it's 0, it converges in one iteration. Okay, and you can take the log, and then that's where you start to see this linear convergence. And you can run this, I think it's called log run error bound if you want to do that. Okay, so here's the quadratic convergence of Newton-Kontorovich. There you go, okay. Okay, so it's, what are we doing? First a few iterations, successive approximations, and then first Newton-Kontorovich, then another one, and you see the quadratic convergence where we take the log of the error bound. Okay, so now the question is, when do we want to switch? So here's kind of a heuristic. Suppose that we start with a true expected value function plus a constant. Okay, so and then try to do successive approximations. Now we recover the entire shape of the value function or expected value function, but up to a constant. So here's the error bound for my first successive approximation. I take my starting value times the starting value evaluated at the Bellman operator. So it's like, this is the error bound for the first successive approximation, these numbers that you will see here, right? Okay, now this was just equal to a constant, right? The initial value was equal to the true expected value of the plus a constant, so we'll just put that in. And if you kind of continue going through that, you end with 1 minus beta times this constant. So yeah, why don't we just do another iteration? So, it's not 0 yet. We want it to be 0, so we've solved the Bellman equation. We do another iteration, and you kind of continue doing that, you get beta times 1 minus beta times this constant. And what you see is if you divide these two with each other, you get exactly beta. And so that's kind of an indication that you're going to recover the curvature of the value function, but up to a constant. And that's happening a lot. And if you just continue doing successive approximations, if beta is very close to 1, it's just never going to converge. It's just going to stick around with that constant. But Newton will just immediately strip away that irrelevant constant and converge in one iteration. So that's the power of that. So here's the Pauli algorithm. You do start with successive approximation, but then when this relative tolerance get close to beta, then you switch to Newton, do a few Newtonist steps, and then you're done. Okay, analytical derivatives. And let me see how I'm doing on time. We want to talk about cars as well, and we are 41 out of 100. Okay, so 40 minutes left or something? Yeah. Okay, so all I want to say here is you ought to calculate the analytical derivatives of the Bellman operator, so you can calculate the derivative of the likelihood function. And it's not that, well, you need to do that anyway for the Newton-Kantorovich iteration. It depends on this derivative of the Bellman operator. And turns out to be very simple, right? It's just beta times the state transition matrix. So it's not like the end of the world to calculate this. Okay, and it's one line of code in MATLAB, so why not do it? Okay, and so here's the code. And there's similar code both in MATLAB, Python. Okay, I'm an old fart, so I used to do MATLAB. And then you can provide analytical gradients of the likelihood. And what we'll do here is it's like back propagation. That's what they call it, right? With the neural nets. It's really just a chain rule, right? So we look at the gradients of the likelihood function. This is just the derivative of the likelihood function for a standard logit, right? But then we want to have the derivative of the choice-specific values. How do you do that? Well, you take these partial derivatives, but the problem is it depends on the derivative of this integrated value function. This is trivial to compute, right? It's just derivative of the utility function. But this one we need to calculate the derivative of. And so how do you do that? Well, John told us the value function, the expected value function, or the integrated value function is implicit functions of theta. So we can use the implicit function theorem to calculate those derivatives of the fixed point with respect to change in the parameters. And that depends on, oh my God, this is what we need for Newton-Kantorovich anyway. You see here how you kind of, just build stuff on top of each other. Okay, and then that's the one we have down here. So you just, reuse things you need to use anyway. You put all that together, there's the code, and then it's going to work pretty quickly. Okay, so here's the last thing that's worth thinking about when you do maximum likelihood, especially of discrete choice models. Use this Berndt-Hall and Hausman algorithm. If you don't want to calculate second-order derivatives of the likelihood function, utilize that. It's maximum likelihood, say information identity should hold if the model is well specified. So the outer product of the gradients is a very good approximation for the Hessian. So you only need to calculate first order derivatives. And so we just replace this guy here with the outer product of the scores. It's just the first order derivatives. And those we already have, right? So we're done. So that's the additional advantage that's very nice also because here, this is essentially a quadratic form. So it's always positive definite, which means you always move in the right direction towards the top, even in convex areas of the likelihood function. Whereas here, Newton would just take in the wrong direction. Okay, so I'm not going to talk more about that, except that this guy tells us we should, that's the way to the top, right? Use BHHH. Okay, so doing that, now it takes not like several minutes, and it converges pretty quickly. So here it was like 0.7 seconds. And we did that comparison. Yes?
Power of the BHHH concentration possibility, right? Because you may be at a point in which the Hessian is not positive or negative from definite, right? And the BHHH will still give you valid standard error, right? So your algorithm may not have converged, but if you just use that, then you wouldn't notice, and the audience of your seminar wouldn't either, right? Whereas if you try to get the Hessian like numerically or analytically, you would see that some diagonal element is negative, for example, and then they would complain while trying to where we were standard error.
Well, we are making all sorts of approximations already. So, the Newton's method is based on a quadratic approximation. The function may not be very quadratic in the first place, and then we say the Hessian is giving us it's giving us the curvature of this quadratic, and then you try to maximize that quadratic. We're making all sorts of approximations. You're right. This approximation is much better further away, or not close to the true parameters as n go to infinity if the model is well specified and all that. Okay, so it's only when the information identity hold. My experience is that this B is pretty powerful, even when you start it further away. Okay, so often you combine with some sort of line search algorithm, and B always take you in the right direction. Okay, it may take you too far, but then you like take half the step, and then you half the step again, and then you get there.
Suggestion or any sense to what, like, how to understand whether we are really like those terminal, or if it's just like the regularization that we're doing that is helping us converge. I don't know if the question is there.
I don't have an answer right now. I think in the interest of time, kind of we need to move on. But I'll have to talk more about it. I don't have an answer right now. Okay. Anyway, so we did. I just want to conclude with this. Would say, okay, we did the comparison. Here's so this table I showed you for Shu and Judd. Essentially, what we find out is that if we do the successive approximation and Newton iteration implementation of the nested fixed point algorithm, you look at the computer times, it's actually the same computer time as you would get with AMP, with MPEG AMP. So implementation matters. That's the point I want to make. And it was my chance to go in detail through the nested fixed point algorithm. Not to say that MPEG doesn't work. You can see it works. Okay. It's just another way of approaching the problem. Okay. So cars. Okay. So this is, and you can say this is like Harold Zucker and steroids. Okay. So now we have a bigger state space. Okay. We want to figure out, how to replace our cars. And, these are very expensive. In Denmark, where I come from, and cars are very expensive. This is a Volvo. We like Volvos, but see, the problem is this is like $200,000, okay, in Denmark, because we pay a lot of taxes, okay, and in the U.S. we pay $60,000. Okay, so you look throughout Europe, we're just like Denmark kind of stands out as the most expensive place to have cars. Because we have all these taxes, okay? So what we want to use this model for is to evaluate a reform where we change those taxes, okay? And maybe change the balance between registration taxes and usage taxes or gasoline taxes. Okay, so here's a few facts. It generates a lot of revenue. It's like 2 to 3% of GDP, 4 to 7% of the tax revenue, which is high in Denmark. And most of that tax revenue comes from taxation of ownership and these registration taxes. So we have like at that time in the sample period, it's like 180% in registration tax, and then on top of that you pay 25% value-added tax. So, pay tax of the taxes too. So that's a lot of money. And so we want to figure out if this registration tax is in some sense over the top of the Laffer curve. So in order to answer that question, we need a model. And so that's what we do. We're in the model with car, a model where consumers choose which type of car to buy, okay? Could be Volvos and other types of cars. So there's going to be the different types of cars, and there's going to be different ages of cars, because cars are aging as well, okay? And so then the consumers decide how much to drive, and then they also make their ownership decision. So that's purchasing, replacing, trading, strapping. This is forming all the discrete choices that no longer binary. Okay? I'm going to show you the tree in a second. And then in equilibrium, there are going to be used car prices that are determined to equate supply and demand, because people can both buy new cars and used cars, and this model predicts the demand for all these different cars, but also to predict the supply, because if I have a car, I put it on the market and sell it, someone else is offered that car. Okay, so here's the idea. Now we have like a 3-ring circus, right? Before it was like a 2-ring circus. You search over the parameter space, and then you repeatedly solve the model. Now the model involves equilibrium now. So we're gonna essentially do the same outer optimization with maximum likelihood, and then it's going to be an equilibrium solver where we find the prices that kind of clear the market, put excess demand equal to 0. I'll come back to that. Okay, but before we do that, we need to figure out how to even calculate demand. So that's the first thing. So that involves, for each parameter vector, each price of used cars, we solve the replacement problem or the trading problem for each of the agents in the model, given the prices. Now, given that, we can calculate the state transitions implied by these decisions, both trade transition matrices and aging transition matrices. That tells us how the fleet is aging. And then we can calculate a stationary equilibrium there, just like we have stationary equilibrium in the Harrell-Zucker model. Okay. With that, we can calculate the excess demand. So all of this depends on essentially on the prices of used cars, because that determines the trading behavior. And implicitly, that also determines the equilibrium distribution of cars. And in turn, the excess demand. So that's kind of the plan. Okay. So here's the choices. So you can purge the car. That is, you get rid of the car. Okay? So you choose essentially, if you have a car, this is for a consumer that has a car, you can just get rid of your car without getting a new one. And then you have a choice whether you want to scrap or sell the car. You can also keep the car, and then you don't have to scrap or sell the car, put it on the market again. And then there is the choice of replacing the car and buying a new one. And if you do that, you choose what type of car to buy, what's the age of that car. And you also have to choose, do you want to keep your car or scrap it? So sell it on the secondary market, or you want to scrap it and just put it on the scrap yard. So if you sell it on the secondary market, it kind of adds to the supply of cars. Okay. Now this is just a discrete choice model, just like Harrell-Zucker. It's just more than two choices. It's all these different choices. It has the same structure here. So here's the choice specific, or here's a value function now. Also, again, conditional on the epsilons, but I'm going to integrate them out in a second. So there's going to be a max over all these different groups of choices, keeping or purchasing the car or trading the car, and then each of these has choices in themselves. Okay. So you wake up in the morning and look at your states, and you make choices. So this is going to be the state of the car. That could be, what is the type of car I have? What is the age of the car I have? That determines the value functions. And then all these value functions are presented here. Okay. So let me see how much time I have. 25. Okay. So why don't we just look a little bit at these value functions then? Let's just start from the top. Here's the value of purchasing and scrapping the car. So this is the state. Okay? This is your decision. And this is the current utility and the future expected utility. You kind of have already embedded the state transition in conditional on these choices in these equations. So you get essentially the utility of no car. So empty set just means no car. Okay? And then because you choose to scrap the car, whatever car you have, you're going to get the scrap price, which is P under bar. That depends on whatever type of car it is, so it's subscripted I. Okay? And then there's a marginal utility of money. It's a parameter we estimate. Now that's for today, but tomorrow you're going to get the discounted expected value of having no car. So what else could you do? Well, you could put that car in the secondary market, in which case you would get the price, the secondary market price of whatever car you have, right? So this is a consumer with a car type I, HA, so you're going to get the price for that. And then there could be potential seller's transactions cost involved, and we're going to try to see if we could estimate the parameters of that. The result is going to be the same tomorrow. You're going to get with no car, okay? Whether you scrapped it or you put it on the secondary market. And then there's going to be more. Here's this is the value of keeping. If you keep your car, well, you get to the utility of having that car again, right? And then it's only tomorrow that car is aged 1 period. Okay, so it's 1 year old. Same car, still type I, but it's just one year older. There's a little probability that it kind of falls into an accident or it's just exported. That happens just exogenously. So that's why we have this additional expected value function. What is this? This is the value of trading whatever car you have today for a new one, okay, of type J HD. And now you got to get the utility of that new car right away. So this, once you buy the car, you just get it right away, okay? But you have to pay for the difference between the scrap price because you chose to scrap it and the price of the new car. Just to kind of see where I'm getting. Okay? There's some trading expenses. That could also include buyer's transactions cost. And here you have the whole 9 yards. If you also go in the secondary market, it's going to be seller's transactions cost as well. In either of those two cases, the car that you bought is just going to be aged 1 period in the next period. So all these different choices and combination choices corresponds to different parts in this tree. Okay, now it's still tricky, right? Because it depends on all these epsilons, but fortunately, additively, generalized extreme value. So this guy here, we can calculate, and it's going to be the log sum. Actually, in the paper, it's some recursive log sum because it's a nested logit. Okay, but let's not go there, right? So right now, we just assume extreme value all the way through. So once you have that, well, you see that depends on all these choice-specific value functions. So you can see for a given vector of or given price vector, you can calculate those expected values from all these by taking the log sum of all these different choices. Okay, and now you're back in business, right? Because now for a given price vector, it's just a mapping from expected value functions to expected value functions, no epsilons left. Yes?
When you say scrap, is it really like breaking the car? Yeah, you can tell, like, of course, not you, like some company, but.
So you're thinking about this guy here.
Yeah.
Okay, there's 2 types of scrap. That's what we call accidents or exogenous scrappage. Sometimes cars disappears for no reason. We need to have something like that in the model. Like even like 2 or 3 year old cars just disappears. It just doesn't make sense that this was endogenously scrapped in a way where the agent would be maximizing utility. So that's why we have that. The other thing is endogenous. Okay, so that depends on the how old is your car and what is the current set of the prices. It's not in the secondary market if they just becomes clunkers and disappears. Yeah?
So is the utility function contains the externality of the total number of cars in the country? So what I'm saying, so
Oh, no, you're thinking about like congestion externalities and pollution and so on. Well, we kind of add that at the end of the back of the envelope as,
So the reason why I was thinking is the research question itself is started as like, what if the new tax policy has been introduced? And I think the taxation affects like the total number of cars.
Yes.
And I think the utility function itself is just considering the individual.
Okay, so there's a question here about if people are taking into account the all the negative externalities involved with their choices. No, they're not. Okay. But if we want to do policy evaluation, we can calculate counterfactual from the model, see what people do, how much they drive their car, what type of car they buy, and then we kind of use other numbers to calculate those things you worry about. Okay, I should probably get to the end. Okay. Okay. So let's just say now in principle, we know how to solve this model, okay? So given this model, we can calculate state transition matrices for the for the market. Okay, so let's just state a few assumptions. Okay, so we're going to have an infinitely elastic supply of new cars. You can always buy new cars. This is not endogenous. We have another paper coming where we have Bertrand price competition, where these would adjust to the the utility consumers and so on. So, but not now. This is just exogenous. And then there's also exogenous prices for the scrap price. We're just going to take that as given, but then try to solve for all these endogenous used car prices. Okay, and so before we go there, let's just take a definition here. This is the ownership distribution. So essentially here, this is the distribution of who owns the different cars. You can have no car, you can have different types of car, one up to capital J. And so QIA is a fraction of consumers who are holding a car type A of HA. Okay. Okay. So here's the equilibrium. So we're going to assume that consumers are maximizing discount expected utility. They are doing the Bellman equation stuff. That's what we just been through. And then the secondary market is clearing for all tradable cars, putting supply equal to demand. And then we're going to assume that this ownership distribution Q here is a stationary distribution. So how is the dynamics of this ownership distribution governed? It's by the state transition matrix. Okay, so there's going to be, that's determined by the conditional choice probability, determines who is buying, who is selling. Okay, so in order to calculate this state trade transition matrix, you need to solve the model for a given vector of prices. And so here's how it looks. This is our state transition matrix, and all these different triangles here is essentially composed of conditional choice probabilities. So for example, like this is a conditional choice probability of remaining in no car state. That's one particular transition. And then you have like, here you have the probabilities of keeping the car that's like being on diagonal. People are keeping the same type of cars, and all these different conditional choice probabilities kind of tell you how the evolution of the car fleet is changing over time. So we can calculate that given the conditional choice probabilities. And so what is this? This is the distribution of cars after this trading phase. So here's what's going on. Well, the cars are aging as well. So after the trading phase, then they are aging, and then they're kind of ready to look at the distribution of cars next period. So you wake up in the morning, look at the ownership distribution of cars, then there's a trading phase. That depends on the conditional choice probabilities, and then there's the aging phase. That is just physical aging of the cars, according to this physical aging transition matrix. And so that's kind of the process. So you start with Q, there's trading going on, and then there's aging, and then what we're assuming is that we have a stationary equilibrium. Okay. And so we just need to essentially find the ergodic distribution to this joint aging and state transition matrix, or to the state transition matrix. And that's give us Q for a given value of the prices. Now, Q is now a function of those prices, right? Because every time you change prices, you get a new set of conditional choice probabilities, and that gives a new trading matrix, and therefore also a new fixed point. Okay, then there's supply and demand. And it's not that magic. Here's demand, here's supply, put supply equal to demand, and then you solve for P. So what is demand? Well, demand is going to be all the people who want to buy cars of this type, either if they don't have a car in the first place, or if they have some type of car, and then you multiply with how many people who own that car, you aggregate up. That's demand. So it's just aggregating conditional choice probabilities using this equilibrium distribution. On the supply side, well, it's going to be all the people who are not keeping their cars and who are not scrapping their cars, multiplied with how many people who have owned those cars. That gives demand for this particular type of car. Of course, it depends on the prices and those quantities, which in the end also depends on the prices. And so now you have a system of equations you can solve using Newton's method. And see, that's essentially what we are doing. we are solving this models, computing state transition matrices, finding the stationary distribution. Everything here just depends on the prices. We end with a system of nonlinear equations, and then we want to solve that. Well, we can again use backpropagation with the state chain rule again and again, calculating derivatives of the excess demand, calculating derivatives of this, and so forth, all the way back in a similar way that we've done with the Harrell-Zucker problem. Okay, so that's why it's really, really nice to have something you could differentiate. And it may look a little bit, daunting to calculate all these derivatives analytically. We did that in MATLAB, but then Max came in and said, no, let's just let JAX do that for us. All that automatic differentiation. There are things you have to do manually, like calculating using the implicit function differentiation, but all those partial derivatives, you just get that for free nowadays. Okay, so we're solving this nonlinear system of equation using gradient-based solvers, okay? And we show that everything here is smooth. We calculate analytical derivatives, and then we also have a simple version of the model where there's no heterogeneity or anything, where we can solve for prices in closed form using linear algebra. So we have good starting values. So these, and so we make extensive use of Newton's method for solving the dynamic programming problem. We also solve those by Newton-Kontorovich iterations for solving for the equilibrium prices and then for maximizing the likelihood. And then, of course, again, I'm going to insist on using the information identity to do the BHHH algorithm. And then repeatedly use of the chain rule. Anyway, we add some heterogeneity. The different consumer types doesn't really change a lot. Okay, we just aggregate market clearing conditions up, and then we essentially impose stationarity by different types. So this kind of a detail. Okay, here's John. So finally, he's with us. And this is what this model is about. This really like gains from trade here. And this is real data. Because I was visiting John, and then I didn't have a car. But John was about to replace his car, and he got this one and sold this one for me. So, and you see how happy they are, right? There's gains from trade. Okay, he's happy about his new Volvo, and I'm actually really happy at being able to drive around in Washington. So that's pretty good. So here's a little illustrative example from this model, just a simple model. We're doing the full structural estimation of it. So, but this is just a little illustration here of with high and low transaction costs. So this is just a fraction of consumers that owns cars of different ages. So you have different car ages here, and you have, it's just a histogram. So there's two types of consumers. Blue, that's John, right? That's a rich guy, and then there's red, that's me. And see, in this economy, the poor consumer is kind of sorting into the older vehicles. And then if you had introduced transactions cost, what's going to do? It's going to drive the poor consumers out of the out into the outside good of having no car. Okay. But it also reduces John's joy or John's probability of actually buying a new car because he's kind of dependent on sending it down the food chain, right? And that's what you're shutting down when you add transactions cost into this economy. We can also calculate here the prices that comes out of this little model. And I think if you go and do the MATLAB code here, it's some MATLAB code to solve this run illustrations, just to get, like this, then you can kind of replicate this. And this code for replication of this model is oh, there you go, there one. Okay, so we solved the model. I just want to say the code for replication of the paper is in the repo. Okay. Okay, where did we go? We want to take this model to the data now. Okay, so that was kind of the first loop, right? Search over the parameter space. I haven't even said what the parameters are. Oh, yeah?
Sorry. So y'all aren't endogenizing like fuel prices in this sort of usage decision. So it's like, what if you replaced high transaction costs with just a high fuel price? Like, would it be the same?
Fuel prices are not even in the model yet, but they're going to be in the model we take to the data. We just take the fuel prices that were observed. So we're not, we're going to consider shocks to the regulation of prices. Put tax and fuel. Anyway, let's just do the estimation, talk about the mechanics. I have a few minutes left, I believe. Okay, so we do now the doubly nested fixed point algorithm. Okay, so we get data on all these transactions, all the choices that Danes are making, like when they're, depending on the car type they have, the car age they have, that's the state, and what consumer type they are. Okay, they're going to make all these different purchase decisions. We observe all these discrete choices for the entire population of Denmark over time. Okay, and then we're going to essentially maximize the likelihood that's kind of derived from this model. So here the conditional choice probabilities. But every time we do that, we need to not only solve the consumer problem, but also solve the equilibrium problem. So we impose these equilibrium constraints. And the reason why we do that is because we don't observe the prices of used cars. So we kind of have to back those out, and that's coming out of the model. So we're imposing equilibrium because otherwise we don't have these observed prices. We have a future version of the paper where we have prices of used cars. So then you don't have to do that. Okay. So let's see. Okay. So we want to take this model estimated on Danish register data to evaluate the effect of this reform. We lower the registration taxes and change the price of gasoline. Okay, so we need now to come with a parametric specification of utility or the payoffs. Okay, so here there are going to be some utility of car services that depends on the age of the car and some driving. Otherwise, you don't have any utility of driving. How can we affect the trade-off between the cost of gasoline that we want to tax and then the registration taxes? So here's the ownership utility. That's just quadratic in the age of the car. And this is going to be heterogeneous across all the different types of cars. Okay, so this depends on the different parameters. Then there's utility of driving, and we derive that. We have also a quadratic utility of driving, and that gives like a linear demand. So the way we're going to proceed is we're going to try to estimate these demands in a first stage. So here's the structural driving equation implied by the first order conditions. Differentiate, put equal to 0, you get linear demand. And so here's like the structural driving equation, which is entirely static. And you see here, it depends on some reduced form parameters. We're going to estimate those just with linear regression. Okay. And then afterwards, we're going to plug that right back into the utility function of the discrete choice using the optimal level of driving. Essentially, I think Bob is doing something similar with the consumption choice, where he kind of backed out what the optimal level of consumption was. So that gives us an indirect utility function. And now, given these parameters here, we have we're back in a discrete choice model world. And so we can estimate with this nested fixed point algorithm. So here's the procedure is first we do least squares estimation of these reduced form driving equation parameters. Then we do the doubly nested fixed point algorithm to estimate the coefficients of the indirect utility, these U's here. Okay. Now, after that, we can, given these reduced form parameters, we can back out what the structural parameters were, simply just inverting these equations or solving the set of equations. So that's what we do, and we need to do that to do counterfactuals. Okay, so the model fits the data, and I don't think there's a lot of insights here. You know, poor households are more likely not to have a car, and they're buying cheaper cars and so on, right? So it's like what you'll expect, okay? And there's a natural preference ordering. And also the model fits data pretty well. So let's just, you know, kind of, you trust me that's the case. So here's the observed ownership distribution for different types of consumers. So here they are. This is like a light browns, like a very dirty car, and light green, little green car, more fuel efficient. There are different types of cars, and then there's no car. This is the data. This is how the data looks. Okay, and you see the cars are kind of disappearing from the fleet, right? That's the age. This is the age of the car. Here's a model. Okay, here's the data. Here's a model. Okay, so we're convinced, right? If you look at it another way, here's the observed sorting. Here's the predicted sorting from the model. Okay, so you know this is reasonable. Okay. Okay, and then we can also use, given we have estimated the model, we can calculate the implied equilibrium prices for different types of cars here. Okay, you see the nice downward sloping. What's the zigzag? That's because there's these biannual inspections in Denmark. And it's kind of costly to go those. Then we want to do the counterfactual. And I guess I have a couple minutes, 2 minutes. Okay. So what we're doing now is we're considering different types of counterfactuals. Here's a baseline. This is just a prediction at the baseline. Okay, so this is the fuel taxes in the baseline. It's like, you know, a little bit more than 50% of the price of the pump is taxes. And then there's a registration tax at the top bracket is 1.8, so 180%. And we want to see what happens if we have that tax. Okay. Now we consider different policymakers. One that's just assuming, because now you change the price or you change the registration taxes, that changes the prices of new cars. You expect that also to change the prices of used cars as well, right? And so you need a model for like ours to predict what happens. And so if you don't have an equilibrium model, well, you know, maybe we'll just assume that the changes proportionally. That's what we call the naive policymakers. So everything just drops proportionally. So that's what's going on here. That's like the naive policymaker. And so the policymaker here want to do a budget balance reform where it still get the same tax revenue. Okay, so where's the tax revenue? So over here, tells me to stop. Okay. And you know, by construction, this is balancing. But now we see, okay, what happens if the policymaker actually look at what the consumers did using the equilibrium prices and say, okay, here's the tax revenue that we thought we would get. Oh my God, we're like lots of money is leaving the Danish budget. Okay, so that's why we also calculate the sophisticated policymaker and see, okay, given that he realizes the equilibrium distribution of the used car market needs to be in equilibrium too, find the optimal policy. Anyway, we can do different types of equilibria. Last thing I want to show is this Laffer curve. If you change the car tax and the fuel tax at the same time, then you can kind of trace out what the Laffer curve is. This is where we were in Denmark. Very high registration taxes. Okay, so that's just a baseline. Okay, that's where we have one. Now, if you decrease the registration tax, you see you get more tax revenue. If you decrease the registration tax and increase at the same time the fuel tax, you give even more. Okay, And these two taxes have different effects on consumer welfare and on, say, CO2 emissions. Of course, if you change that balance, if you make it cheaper to buy cars and more expensive to drive them, they're going to drive less. Okay. So here's a graph of how the CO2 emissions would be as function of the fuel taxes. If you increase the fuel tax, well, people are going to drive less. So wow, increasing that direction. So lower fuel taxes, more CO2, lower car taxes, more CO2, okay? And welfare, well, people don't like taxes, okay? So higher welfare. But see, the cool thing is there's actually an area where you can both get higher welfare, lower CO2, and more in taxes. And that's what we do in this figure. We are essentially making a contour plot of all these different graphs derived from the structural model and calculate different areas. So here inside this area, you have the here you have a constant tax revenue. So it's increasing as you go further in, and here's the top of the Laffer curve. Okay, here is the welfare constant. Okay, but if you lower the taxes, people are going to get higher welfare. And so here is the CO2 emissions. If you lower taxes, there's going to be more pollution. Okay, and so there's this sweet spot where you can get essentially all the desired outcomes. Okay, essentially higher welfare, lower CO2, and higher taxes in Denmark. So I'm going to end it with that. Sorry for going a little bit over time.